How about now? All right, that's great. Her previous speaker must have, must have turned it off. All right, so I'll be speaking about W-algebras, modular of sheaves on surfaces, and AGT. The main thing, like a starting point of this talk, is the famous Haldai-Hayoto-Hachikawa correspondence, which I'm pretty sure everyone in this audience has heard quite a lot about. But let me just say that this is a correspondence between two different type of theories. On one hand, we have a 4D gauge theory, and the gauge group will always be UR in my talk. And on the other side, we have a conformal field theory, specifically KR-1 Toda field theory. So I'm pretty sure, like I said, that you have heard quite a lot about this correspondence. One of the fundamental predictions of this correspondence is that the Nekrasov partition function corresponding to the theory in the left-hand side should be matched under this correspondence to conformal blocks for W-algebras of type GLR, which is the symmetry algebra of the theory in the right-hand side. So I don't want to give a physical introduction to this particular correspondence, as I'm pretty sure everyone here has seen it quite often. I think I would like to convey today is a mathematician's introduction to the correspondence, and specifically to show you a perspective which comes from algebraic geometry. So there will be a lot of algebraic geometry in this talk, and I will try to translate everything in that language, or as much as I can in that language. So mathematically, I should say that quite a big chunk of this correspondence was established by Maulik and Akunkov independently. And that, I think, happened independently around 4 or 5 years ago, something like that. So their mathematical take on AGT is to define an action of a W-algebra of type GLR, so the object which corresponds to the theory in the right-hand side, on the cohomology group, which I will call H, of the moduli space, which I will call M, of sheaves, canned, or instantons on A2. So here throughout this talk, I will be tacitly using the celebrated correspondence between topological instantons, which are vector bundles with a flat connection, canned sheaves and algebraic sheaves, and everything in this talk will be in the language of sheaves. Like, just to paraphrase a proverb, when all you know is algebraic geometry, everything looks like a sheaf. So in this particular talk, everything will be a sheaf. So I should say that, well, the fact that our instantons are points in the moduli space M is obvious. Why is the cohomology group H playing a role here? So the cohomology group H is playing the role of the Hilbert space of the theory. And specifically, the Nekrasov partition function is the integral of a certain cohomology class on this moduli space. So if you want to understand the partition functions of these various theories, it's enough, or it's a mathematical version of that understanding, to understand the cohomology group H and to understand what it means to integrate. So in other words, you have to understand what for me will be an abelian group and a linear map on this abelian group called integration. And that bridges the problem with representation theory. So one of the upshots of the work of these groups of mathematicians was to say that in the pure gauge theory, the Nekrasov partition function which we want to compute can be calculated as the norm squared of a certain cohomology class called 1, which in terms of cohomology, it's just a unit cohomology class, or if you want to think in terms of homology, the moduli space is smooth. So the unit cohomology class is Poincare dual to the fundamental class, and by taking the norm squared of this particular class, you get the Nekrasov partition function. So that connects this business with the theory in the left-hand side. Now, as far as the theory in the right-hand side is concerned, they show that the cohomology class 1 is what physicists called a Hayoto state. In other words, it's uniquely determined by how the W-algebra acts on it. So you can completely describe this class in terms of both the gauge theory in the left-hand side and the conformal field theory in the right-hand side. And this shows that a Nekrasov partition function is equal to conformal blocks. So this is the philosophy which they carried out in the case of the pure gauge theory. And my goal today is to give a parallel description of what happens from a mathematical viewpoint in the case with matter. So the matter which we will encounter in this talk will be a bifundamental matter. So that's a bifundamental representation of a product of two gauge groups. And the contributions of these particular matters are encoded in terms of algebraic geometry in the so-called Hext operator, which was studied and introduced by Carlson and Akunkov. So I'm pretty sure you've seen this operator, but I would like to present it in a mathematical language. And the way we present operators on cohomology mathematically is by correspondences. So let me take a couple of minutes to actually write down a correspondence diagram, since it's one of the things we will see again in this talk, and I think it's one of the most important things for doing computations in cohomology. So we have this Hext operator, which is an operator between the cohomology of a moduli space. So it doesn't really matter which moduli space we have here. You can think of the fact that this is any algebraic variety, and you have a cohomology, and you take its cohomology group, and you want to define an operator from cohomology to cohomology. It doesn't even matter that these spaces are the same. It's just a coincidence that this is the case in the case at hand. How do we define such an operator? The thing to do is to draw what is known as a correspondence. So you put a space in the domain and a space in the codomain here. You write their product with projection maps P1 and P2. And now, to give an operator from the cohomology of this space to the cohomology of this space, what you have to do is to give a class on the product here. And in this particular case, a class we will be looking for the vector bundle, whose fibers are the space of extensions between sheaves or instantons F prime and F. This is a vector bundle on the space M times N. I should say that the sheaves I'm calling F live here. The sheaves I'm calling F prime live here. So points in the product are pairs of sheaves F comma F prime. And the fiber of this vector bundle above a point parametrized by sheaves F and F prime is the space of extensions. You can think of this as a vector space, even though it's actually a complex of vector spaces. But you can think of this as a vector space whose fiber above this point is this particular X group. So what they say is, take this vector bundle on the product, look at its Chern polynomial with variable m. You can think of m as a complex number, if you will. It will be interpreted as matter in the physics. With this datum, you can define an operator from the cohomology of this to the cohomology of this by pulling back a cohomology class, multiplying by the Chern polynomial of this vector bundle. In principle, you could multiply by anything. It just so happens that in this case, we're looking at a Chern polynomial of a vector bundle, and then pushing forward via this other map. So this is known as a correspondence. The idea that a cohomology or K-theory class on the product gives rise to an operator between cohomologies of these two spaces. So it's a fact that the contribution that you can work out what the partition function various quiver gauge theories with bifundamental matter are by studying this operator and studying in particular its matrix coefficients. So as a consequence of an analysis which physicists know quite well and I will not necessarily present here again, you can actually prove very mathematically AGT for linear quivers if you present the operator AM as an intertwiner for the W-algebra action. So I mentioned in the previous slides that people write W-algebra actions on the cohomology group H. Well, it just so happens that this operator AM will behave like an intertwiner for these representations. So it has a representation theoretic interpretation. So in particular, if you want the Nekrasov partition function for a cyclic quiver gauge theory, then what you have to do is to string n of these operators AM in a cycle and take trace. And the trace of the composition of AM operators will be the Nekrasov partition function of the cyclic gauge theory. So that's one of the things I mean when I say that this particular operator encodes the partition functions of high fundamental matter contributions to quiver gauge theories. So I want to prove this fact. I want to prove that this particular operator is an intertwiner for our W-algebra, since, as we have seen, this will be a mathematical incarnation of AGT. So I'll do this by the following steps. So first of all, I will Q-deform everything. And this is not just a matter of deformation for the sake of deformation. It will turn out that my computations and my proof are easier in the Q-deformed case. It's actually easier to prove them in the Q-deformed case, can then obtain a classic limit by just sending Q goes to 1 and taking leading order terms. So I'll Q-deform everything. I will redefine the W-algebra action in a way which is different from the ones that we have seen on the previous slide. We haven't really seen them on the previous slide, I just stated them. And in the end, I will prove that the operator AM commutes in a certain sense with a W-algebra action. So I'm putting the words intertwiner and commutes in quotes because it doesn't commute on the nose. It will commute in a specific way, which I will show you in a few slides. So there's a particular formula which says how AM interacts with generators of a W-algebra action. So here's one thing which I would like to convey in my talk. One of the upshots of my construction is that it's completely geometric. And because it's completely geometric, we can make sense of it for surfaces, for algebraic surfaces, which are more general than the affine plane. And this is, I think, a significant point I'm trying to make, because a lot of the physics literature I have seen about this particular problem uses a certain basis of cohomology and K-theory, which is indexed by partitions. This basis is called the AFLT basis. And from the point of view of algebraic geometry, it comes from the fact that there is a torus action on A2, which induces a torus action on the moduli space of sheaves on A2, which has isolated fixed points that are indexed by partitions. And we'll see this in a few slides explicitly. But what this is extremely specific to the case of A2. For a general surface S, you cannot expect such a torus action, and you cannot expect to apply equivariant localization in algebraic geometry, which also means that you should not expect such a nice basis as the AFLT basis. And doing things more geometrically is the only way that I know right now of overcoming this particular problem. So there will be just one slide about general surfaces at the end, unfortunately, but I hope to have time to get there. So what is deformation? I mentioned on the previous slide that I'll be Q-deforming everything. So in this particular talk, deformation will refer to two particular processes. The first of these is replacing cohomology by algebraic K-theory. So I'll say exactly which K-theory I will use in when I define the moduli space M in more detail. But you should think of this as being the equivariant algebraic K-theory of the moduli space M. And the thing which I'm writing in the right-hand side of the equation is just, well, a statement of the fact that a moduli space of instantons is a disjoint union of connected components, and these connected components are indexed by the instanton number. The instanton number is what I call n. So all of the representations, all of the Hilbert spaces that we will encounter in this particular talk will be graded by instanton number, and all of the operators that we will see in this talk will respect this grading. But I will sweep this under the rug for conciseness. So we should always think of a K-theory as being a graded object. This grading has nothing to do with the grading on cohomology. It's just grading by instanton number. So deforming from cohomology to K-theory in physics, it entails replacing four-dimensional supersymmetric H theory with n is equal to 2 by five-dimensional supersymmetric H theory with n is equal to 1, and the fifth dimension is a circle. So this is a very particular case of the philosophy we've seen yesterday in Kevin's talk, where he talked about three-dimensional, four-dimensional, five-dimensional, and six-dimensional theories. It's a particular instance of that. So the other instance of deformation, which we will see, is in representation theory. In representation theory, when you Q-deform things, you replace Lie algebras by quantum groups. And the standard example of that is when you take a Lie algebra G and you replace it by the corresponding quantum group. And we will not see this in this talk. But what we will see is this is a deformation of the Heisenberg algebra into the Q Heisenberg algebra. So a Q Heisenberg algebra, well, in my case, it will be defined over a polynomial ring in two parameters, Q1 and Q2, and I will point out what these means in a second. But the Q Heisenberg algebra has generators called an, which are indexed by integers an, and they have these commutation relations in between them. So let me explain this commutation relation. Well, first of all, Q, and I will write it here because it's going to appear throughout this talk. What I call Q is equal to Q1 times Q2. The whole theory will depend on two parameters called Q1 and Q2, and the most important one of them is their product, which will be called Q. Okay. Second of all, if you neglect these terms here, if your commutator were just Kronecker delta symbol times 1 minus QR to the n divided by 1 minus Q to the n, that is a respectable deformation of the number r. So the expression 1 minus Q to the Rn divided by 1 minus Q to the n is a deformation of the integer r. Now, the commutator over there is more complicated, and there's a reason why it's more complicated. The reason being that Q1 and Q2 are exponentials of the omega background parameters which appear in Nekrasov's work. So Q1 is the exponential of epsilon 1, and Q2 is the exponential of epsilon 2. And this happens because we're studying gauge theory in the full omega background. So that means that you are working on C2, which is equivariant with respect to two tori with equivariant parameters epsilon 1 and epsilon 2. And because of that, everything in the theory, including this commutation relation, will be an expression in these two parameters Q1 and Q2. So if the commutation relation here is a little bit more complicated, it's because of this full omega background, and it's what you have to impose. Okay. Yep. That'll be at the very last slide, hoping I get there. So R is a rank of my sheaves, and it's also a rank of the gauge group. So everything in this talk will be for gauge group UR. So we've seen, well, I've stated how to deform Lie algebras and Heisenberg algebras. In general, the algebra I will want to deform is a W-algebra of type GLR, and the corresponding Q deformation was studied independently by Fagin and Frenkel and Dawata, Kubo, Hodaki, and Shiraishi in the 90s. So this particular deformation actually goes back for 20 years or so, even more. Well, to give you a flavor of what this is, in type GL1, this deformed W-algebra is precisely this thing. So it's precisely Q Heisenberg. So Q Heisenberg, which you see here, is the GL1 case. In the case of SL2, the corresponding algebra is the deformed Virasoro. In the case of GL2, it'll be a tensor product of the deformed Virasoro and the deformed Heisenberg. And for higher R, we will see on the next slide how to describe his algebra, but it will be a more complicated beast. So here's what it is. The original definition of deformed W-algebras is by their free field realization. So mind you, this is not a definition I will use in this talk, but it is a definition which has the advantage of being extremely explicit, and you can present it in one slide, which I think is great. So the Q-deformed W-algebra of type GLR, by definition, is a subalgebra of a big Q-deformed Heisenberg algebra, which I call HR, which is just like the Q Heisenberg algebra before, but instead of having a single family of bosons, it has R families of bosons. So it is the Heisenberg, it is a deformation of the Heisenberg algebra corresponding to the Cartan of GLR, and this is the commutation relation of the defining bosons. Well, how do you define what the Q-deformed W-algebra is? By definition, it is generated by, well, generators called WDK, which are given by this expression here. And I have to say that throughout this talk, the connection between fields, which are expressions like WKX, and generators, which are expressions like WDK to the D, is given by this kind of formula. So in terms of vertex operator algebras, WK of X are fields, the WDKs are their modes. So you will see me going back and forth between saying that an algebra is defined by fields, as defined by their modes. This is the connection between WDK and WK of X's, which we will see throughout this talk. So a definition of the field is given by a certain normally ordered product of exponentials. The parameters you can think of them as being complex constants, even though it's a bit more healthy to think of them as central elements in a W-algebra, but you can assume them to be complex constants throughout this talk. And the claim is, well, a definition is the Q-deformed W-algebra is the subalgebra of Heisenberg generated by the modes of these particular operators, which are the kind of exponentials that people see all the time in conformal field theory. Well, if you look at, well, these papers which I'm citing here, you will see that they work out the following property. These particular fields, WK of X, satisfy relations such as the one which I have here on the board. So the one thing I should tell you to completely understand this, what this expression is saying, is that his symbol that I call zeta of X is equal to 1 minus x, 1 minus x q2, 1 minus x, 1 minus x q. So it's a particular rational function. So if you want to get commutation relation between the modes WDKs, then you take this and you expand it as a formal series in x and y, and you equate the powers of x and the powers of y in the left-hand side and in the right-hand side, and it gives you a bunch of relations. And it's a proposition to say that the Q-deformed W-algebra can be intrinsically defined as being generated by symbols WDK modulo the relations you see here. So these are not called a relation. You have a more general relation when you have here WK and WL, but it looks a little bit nastier, so I didn't have any room to write it on the slide. But it is also a quadratic expression in W. So very importantly, the relations between the generating fields of the form W-algebras are quadratic, which is actually not true of the classical W-algebra. If you take the associative algebras, well, corresponding to a classical vertex operated algebra of type GLR, the relations between the defining fields are not going to be quadratic. They are quadratic in this deformed case, which is very nice, and it makes my life extremely easy, and it makes computations possible. Okay, so this is a definition of the W-algebra, albeit a pretty formula-based one, but in fact, we will not necessarily be needing these formulas. So the thing we will have to do is to do a little bit of representation theory and to define the Verma module of W-algebra. So a Verma module is defined in the following way. Take complex numbers U1 through UR. You can think of these as being formal parameters. If you want, they will play a role of highest weight. The Verma module is defined as the quotient of the whole algebra modulo the right ideal generated by these expressions. So what that is saying is that the Verma module is defined by the algebra acting on the left on a vacuum vector, and that vacuum vector has the property that it's killed by the positive modes, which we expect of Verma modules, and the zero modes, W0K, they act on the vacuum with eigenvalue, which is this expression in the highest weight parameters. So EK is the kth elementary symmetric function. So what this is saying is that parameters U1 through UR, they are encoding the highest weight of this Verma module, or in other words, the eigenvalue of the zero modes on the vacuum. So that's a definition of the Verma module. We will also encounter the Verma module M prime, which is defined in the exact same way, but instead of complex numbers UI, you can think of these as complex numbers ui prime. So in principle, you have such a definition for any choice of highest weight ui and ui prime. So for two different highest weights, you have two different Verma modules, and what I will say makes sense for all of them. So with this definition of Verma modules, let's define the vertex operator. Well, it's a map between one Verma module and the other. And it's defined to be almost an intertwiner of the W-algebra action. So being an almost intertwiner of W-algebras does not mean that it commutes with generators of a W-algebra on the nose, but instead is defined by this property here. So what we see here is a formula for how phi m, a vertex operator, which depends on a complex number, by the way. This is a formula for how phi m interacts with a generating field wk of x. So first of all, you don't take commutator here, you take q commutator, which kind of makes sense since everything is q deformed. M should be thought of as a power of q really, but it's not really visible in my notation. So if this were an intertwiner, this commutator should be 0. It's not 0. Instead, this commutator, which is multiplied by this expression, should be 0. So the u's and the m's and the q's are just constants here. The thing which I'd like to convey with this equation is that this is a q-deformed version of what it means for the fields phi m and wk to be local. This is like the property of locality of fields in conformal field theory, where you have a product of fields, or in this case a commutator, and you multiply them by a difference, and you say that the answer is 0. So one consequence of this formula, actually, in terms of the generating modes, is the following. So you can take the condition in, well, in powers of x, and what it's telling you is that if you take the commutator of phi m with one of the modes, wdk, well, you don't just take commutator, you take this m to the power k deformed commutator, then this is equal to a constant times the commutator with the 0 mode. So w0k. This is just a restatement of the property here in terms of the modes. And this property actually has an interesting consequence, that well, wk is infinite in both directions. So I'm not really sure how to make sense out of it. And actually, a commutator on the nose is not equal to 0. If you set the property that a commutator on the nose be equal to 0, then you overdetermine the vertex operator phi, and it will not exist. So the lemma here is saying that there is a unique endomorphism phi defined by property 1 as we're stating it here. And this is why this particular operator, up to constant multiple, it's uniquely determined. So wk of x is an infinite formal series, and care should be taken when expanding it. All right, so halfway through my talk, here's her main theorem. So in the q-deformed case, as well as in the homological case we saw on the first slide, there exists an action of the q-deformed W-algebra on the K-theory of the moduli space of instantons, and as expected, the K-theory of the moduli space of instantons is isomorphic to the Verma module. So, moreover, a reason why we care about this in the context of bifundamental matter is the fact that the x operator will be equal to the vertex operator up to a simple exponential. And this exponential comes from the following things. So the W-algebra of type GLR is equal to the W-algebra of type SLR tensor a Heisenberg algebra. And that Heisenberg algebra is almost central in the sense that it commutes with SLR. This so-called simple exponential is an exponential in the central Heisenberg algebra, so it's a pretty harmless object. Modulo this pretty harmless object, the x operator is equal to the vertex operator, and this is one of the upshots of this theorem. So in terms of proof, I will not be giving a proof of this, unfortunately or fortunately. So a part about the x operator is a computation in intersection theory. So it's a geometric computation. But to be able to cast it as a geometric computation, you have to give a geometric definition of the first part. So you have to give a geometric definition of the algebra, of the W-algebra action on K-theory. And this is what I would like to give now. So definition. I will give a formula for the generating function of all of the fields of the W-algebra. So this W of xy is, the mother function of all the generators of the W-algebra. So I'm encoding in here all the modes WKD, as D goes over all the integer and K goes over the numbers from 1 to infinity, actually. So there's something interesting in this formula here. So a priori, we have these WK fields only for K going from 1 to R, but we can just define them for all Ks by setting WR plus 1, WR plus 2, and the higher ones equal to 0. So in terms of this fact, we define this generating function of W currents, and we define it as acting on K theory as the following product of matrices. So this dx here is a pretty harmless difference operator, which is responsible for the fact that some powers of q will appear in the formula. If we neglect this dx, which I think morally we could, the operators which I'm calling L, E, and U are certain endomorphisms of K theory, which are defined geometrically, and I will do so in a second, which have the property of being lower triangular, diagonal, and upper triangular in terms of the instanton number. So K theory as a vector space, as we have seen, is graded by instanton number, and the operators L, E, and U are lower triangular, diagonal, and upper triangular. So this formula here, it's not just a definition of the currents it's not just a definition of the fields of a W algebra, it's an LDU decomposition of them, but I call the operator in the middle E because D is taken in this formula. So for the remainder of this talk, I will show you how to define the contributions L, E, and U in a geometric way. So before I do that, I actually have to give you a mathematical definition of the moduli space M. So as I have said, in algebraic geometry, we think of M as being a moduli space of sheaves, but we don't take sheaves on A2, on the affine plane. Instead, we take framed sheaves on P2. So a framed sheaf on P2 is a torsion-free sheaf of rank R on a projective plane, together with an isomorphism of its restriction to a line at infinity and a trivial vector bundle on that line. So that's that kind of isomorphism phi, little phi, not the same as the vertex operator before. The isomorphism phi is called a framing. So we don't just have a moduli space, we have a moduli space with a torus action. And this is the kind of action which I mentioned does not exist if you replaced a plane with an arbitrary surface. But you do have an action of this big torus on M. And this is a very particular case of a moduli of Higgs vacuum, which we saw in the previous talk, and the torus actions on them. Explicitly, the factors C star times E star, they act by scaling P2, and a factor called C star to the power R, it acts by left multiplying the framing here. So it's pretty explicit how this torus acts on the moduli space. Well, because we have a torus action on an algebraic variety, we can consider its torus equivariant K theory. So this will be a group K that I have been speaking about for the previous half hour and haven't actually properly defined it yet. So K is defined as formal combinations of T, formal sums and difference of T equivariant vector bundles on M. So it's something that is quite well known to topologists and geometers. And the only thing that I will actually, well, one of the only things I will need about his group is that it's a module over the equivariant K theory of a point. So Z of Q1, Q2, U1 through UR, it's a space of characters of this particular torus. Any representation of this torus is uniquely is uniquely determined by its character, which is a polynomial in this big ring here. And Q1, Q2, U1 through UR, they refer to the elementary characters of this C star, and this C star to the power R. So you can think of Q1, Q2, and the UIs as being formal symbols. But K is a module over these formal symbols. So it means that you can specialize these formal symbols to any complex numbers, and we can think of the UIs as being complex numbers. And this is a well-defined operation on K. It makes sense to say what it means to multiply a K-theory class by an expression in the Qs and the UIs that just corresponds to tensor product with a T representation. So that's a definition of the moduli space and of the equivariant K-theory. So now about partitions. And here is where I will actually have to write some things down. So everybody knows what a partition is, and I'm sure you have seen in this kind of context R tuples of partitions. I will denote R tuples of partitions by this bold letter lambda. By definition, it's an ordered collection of R usual partitions. The size of the R partition is the sum of the sizes of lambda 1 through lambda R. So actually, let me draw for you a partition in terms of its Young diagram. So a Young diagram of a partition is a set of boxes in the first quadrant of the plane. This particular Young diagram corresponds to the partition lambda, which is 4, 3, 1, because it has 4 boxes on the bottom row, 3 boxes on the next one, and 1 box on the top row. So this is how we connect partitions with Young diagrams, meaning stacks of boxes in the plane. Now, an R tuple of partitions, actually, let me show you in the case when R is equal to 2. Here's an R tuple of boldface lambda. So it consists of a partition called lambda 1. The same partition as before. And a partition called lambda 2, which can in principle be another partition. So this will be lambda 1, this will be lambda 2, and the whole datum of the R tuple of partition lambda will be this whole thing. So that object is called an R tuple of partitions. The reason why we care about them in the context with is that fixed points of this moduli space, they are indexed precisely by R tuples of partitions. And specifically, well, a fixed point in the moduli space is a particular kind of sheaf on the plane which is fixed by a torus, and it's not hard to show that such a sheaf has to be a direct sum of ideals. An ideal is a particular example of a sheaf on P2 or on A2. And I should say that the ideal which is indexed by a usual partition lambda is what is known as a monomial ideal. And here's how you define it. You take a Young diagram of lambda, you put the monomials 1, x, x squared, y, yx, yx squared. You see where this is going, y squared. And you say chi lambda is defined as, well, the sum of C times all monomials not in the Young diagram lambda. So I claim, and it's actually very easy to see, that the linear span of all the monomials which are not in this Young diagram, so meaning x4, yx cubed, y cubed x, y cubed, and all of the other ones, that is an ideal in C of xy, and that's essentially equivalent with being a partition. So is in the context of K-theory because there is an equivariant localization theorem which says that the basis of K-theory is given by the skyscraper sheaves at the torus fixed points. So in other words, a basis of K-theory is indexed by these R tuples of partitions. And in physics, this is called the FALT basis. One more thing before I actually show you some formulas. So I should say that if you have a box in a partition, you define its weight in terms of the location of that box. So for example, in the case of this box, we think of its location of this point, which are 2, 1, and the weight of this box is U1 Q1 squared Q2. So mind you, this box remembers not only its coordinates in the plane, which are 2, 1. It also remembers the fact that this is a box in the first constituent partition of lambda, and this is encoded in the fact that we put U1 here. We also have this box here, which is also a box inside a boldface lambda, but it's in another constituent partition. So the weight of this box will be U2 times Q1 squared Q2. So because of this, we think of this box and this box as being two different boxes. So in other words, an R-tuple of partitions is a collection of boxes in the plane with multiplicities. And we will weights of these boxes in a bit. All right, so finally, I can give you a definition of the LDU decomposition of W currents in a representation K. So the operator E of Y, the diagonal one, is the easiest one. It's multiplication by the exterior algebra of a universal sheaf, and because of that, it's diagonal in the AFLT basis, and it's given by the following expression in the right-hand side. So zeta here is exactly this rational function in here. So everything in the right-hand side, and actually all of the matrix coefficients of all of the operators in this talk, will be rational functions in terms of Q1, Q2, and the UIs. So that's a definition of E of Y. It's rather simple. Now, to define L and U, the other two components of a W-algebra action, we have to consider the following locus. So we have to look not just at a single sheaf, we actually have to look at flags of sheaves. And the kind of flags we are looking for is this correspondence ZD, which flags of sheaves F0, F1, all the way to Fd. This makes sense for any natural number D, together with a point X on the plane. And the only condition we impose here, and this is actually a very important condition, without which this would not have worked, is the fact that all of the successive quotients here are skyscraper sheaves at the exact same points. So in other words, the modifications, the Heike modifications of these sheaves, they all happen at the same point of the surface. And this is actually very important. So what do we want to do with this locus? We want to use it as a correspondence. In other words, we want to use it exactly as here. So it has two projection maps called pi and pi plus d to the moduli spaces M. And the map pi minus, it only remembers F naught. And the map pi plus only remembers Fd. So you have these projection maps onto the smallest piece of the flag and the biggest piece of the flag. And you also have line bundles on this locus. The only one I will actually need is L1. So the line bundle L1, it just keeps track of the one-dimensional quotient F0 modulo F1. So in the definition here, in particular, F0 modulo F1 is a skyscraper sheaf corresponding to a single point. The space of sections of that skyscraper sheaf is one-dimensional, so therefore it corresponds to a line bundle on the locus ZD. A definition of the operators L and U, which are involved in a definition of the action of a W-algebra on K. So they are adjoint. So because of that, it's enough for me to tell you what L is. So L is given as the sum over all these of the operators induced by these correspondences. So how do you get an operator from one of these correspondences? Well, it's in the formula here. You take any class here, you pull it back to ZD, you multiply it by this particular expression, which is an expression in the formal variables x and y, and the only geometric input it takes is this line bundle L1, and then you push it forward, and that gives you an operator on K-theory. The claim is the definition of a lower triangular part of the W-algebra action is the sum over all these of these operators. So, you know, if you like Horace fixed localization, you can actually write down matrix coefficients of this operator in terms of the basis of fixed points. And here's how you get it. So the matrix coefficient of this operator in terms of two R-tuples of partition mu and lambda, well, it's the sum of this big expression here, which goes over all standard Young tableaus of shape lambda minus mu. So what's a standard Young tableau? It's a labeling of the boxes of the differences of partitions lambda and mu with the numbers 1, 2, 3, and so on higher, such that the numbers in the tableau, they only increase as we go up and to the right in the partitions. So for example, in the case of this two tuple of partitions here, here's an example of a standard Young tableau. You can put 1, 2, 3, 5, 6, 9, 10. You fill it with numbers in a way in which you only increase as you go up and to the right. So this is a standard Young tableau of size equal to 17. There's a lot of standard Young tableaus. And what this formula is saying is that you have to sum this big over all of these standard Young tableaus if you want to get the matrix coefficients of these operators in the AFTL, in the AFLT basis. So I should say that this power here is just this power. This denominator is this denominator, and everything else just comes from the normal weights of the maps pi plus and pi minus. So that's where the algebraic geometry comes into the picture, and it's a computation in equivariant localization. All right, here's my last slide, which I actually wanted to be my talk, but I decided to present it for A2 because it's a bit more explicit, and there's not, in terms of formulas, all the interesting formulas are already present in the case of A2. So you can actually make sense of all of this stuff when your sheaves, instead of living on A2, live on a more general surface S. And this is not completely proved because it's based on some conjectures having to do with the moduli space of stable sheaves on S and a W-algebra action, which hopefully at some point in the future we will prove, but I don't have it yet. But I can at least formulate statements and they make sense. So the moduli space M, which was the moduli space of sheaves, of frame sheaves on A2 in the previous case, now will be the moduli space of stable sheaves on S. That's kind of fair. I think you can generalize this to other moduli spaces of sheaves, not necessarily stable, but I don't think there will be so many new features appearing, so that's why I didn't want to do it at the first approximation. So here's how the W-algebra changes. The statement is that you have an action of the same W-algebra action on the K-theory of this moduli space. It has the same kind of generators as before, WdK, but the structure constants of this algebra, which before were just polynomials in two parameters Q1 and Q2, now depend on Q1 and Q2 being, as Andrei said, Chern roots of the cotangent bundle of S. So instead of the equivariant parameters which make no more sense, which do not make sense anymore for a general surface, you replace them with the Chern roots of the cotangent bundle. So to be completely precise here, generators WdK of the W-algebra, they do not give you a single endomorphism of K-theory. Instead, they give you maps from the K-theory of M to the K-theory of M times S. And that's actually a common feature when you have correspondences, because in the correspondence ZD, you have this big flag of sheaves, but you also have this, which is a point on the surface S. And because you have this point here, you have a third projection map from this correspondent to S, because you have projection maps from this moduli space, and to S. You can use this correspondence to produce an operator from the K-theory of M to the K-theory of M times S. So what that means is, if you take any K-theory class on S, you can obtain an operator, you can obtain the morphism of K corresponding to that K-theory class on S. So if the K-theory of S has rank 10, corresponding to each WdK, you will get 10 endomorphisms of Km. Or, put differently, in a way which I like more, you can think of the K-theory of S as being the parameter ring of your theory. So what this means is, you have a W-algebra. You have generators WdK. Any element in a W-algebra is a product of WdKs. The structure constants in terms of these WdKs are polynomials in Q1 and Q2, so you can specialize these polynomials to be anything. In particular, you can specialize these polynomials to be Chern roots of the cotangent bundle of S, so that's kind of topological atom corresponding to the surface S, and that will give you the W-algebra which should act on the K-theory of moduli of the moduli space of sheaves on S. And this rational function here is theta. It also has an interpretation in terms of K-theory, which I will skip. If you're interested, I'd be happy to tell you more about that. And finally, the operator AM is defined in the same way. It's defined as has an X operator between sheaves. The X now is not computed on A2 anymore, it's computed on the surface S, and this parameter M, which was a constant, say a complex number before, now should be thought of as a K-theory class on S. So the healthiest thing to think of it is the class of a line bundle on S, but this actually makes sense if it's a more general K-theory class on S. So this slide is how you generalize everything I have said before to more general surfaces, but the formulas you get, and in particular formulas for the commutation relation between AM and the generators of a W-algebra, they will look the same. So all of the formulas will be universal in terms of these parameters Q1 and Q2. If you want to specialize these formulas for an arbitrary smooth projective surface S, the only thing you have to do is to specialize Q1 and Q2 to be Chern roots of the cotangent bundle of S. Thank you very much. Oh, that'll be a determinant of the universal bundle. So product U1 through UR will be a determinant of U. Well, yeah, so the problem, if we look back here, is the fact that this a generating function of a W currents, it's given by L times E times U. L and U are both infinite sums. So what this means is that each WdK is an infinite sum of operators here. That infinite sum, it converges if you have some kind of stability which is telling you that the instanton number is bounded below. But if you're working on the stack, I have no reason to believe that the instanton number is bounded below. So the right-hand side of this expression will be an actual infinite sum in all representation, and I'm not sure how to define it. So you do have this kind of convergence issues. Thank you.